Hi everyone, we are finally ready to put all the pieces we have learned so far together and solve the consumer's problem to find the optimal consumption bundle for the consumer. This video contains a lot of information. I encourage you to be thinking, taking notes, and watch the parts that you don't get in the first time more than once. So here is the overview of what we will do in this video. We will first define the utility maximization problem, which combines people's preferences and budget constraint. We will then describe how we can find the optimal point graphically. We will first provide some intuition to it, and then there are two classes of solution. One is interior solution, which will be found when the preferences are codouglas and the perfect complement. The other is corner solution, which will be found when the preferences are represented by perfect substitute. I will also describe a special case of utility functions, and those will give us the general conditions of how we find the optimal choice. After we go through all of those, I will solve for the optimal solution for two numerical examples, one for codouglas utility function and the other for perfect substitute utility function. And lastly, I will summarize this chapter. To define the utility maximization problem, recall that we have a utility function representing consumer's preference. And by maximizing, we are trying to find the consumption bundle that gives the consumer the highest possible level of satisfaction. And in our language, we are going to maximize the consumer's utility function. However, without a constraint and under the assumption that more is better, consumers would be wanting to choose infinitely many of each of the goods that they can possibly consume. So they have to be constrained by something, and in our case, the budget constraint imposes what is necessary for this question to make sense. So we are going to find a consumption bundle that maximizes the utility and also remains in the consumer's budget constraint. The such consumption bundle, to note, may not be unique, may not exist in some very special cases, but we are going to study this question in a nice setting where it is going to be unique and it is going to exist. If you take further courses in the consumer theory, you may encounter cases when those two aren't violated. So we call such consumption bundles the optimal bundle. To express this problem mathematically, we are solving the following problem. So how should we read this? So the x comma y below the sign max is saying that we are choosing x and y. And we are choosing x and y to maximize something, where the something is our objective function or our utility function. So the first line is saying that we are choosing x and y to maximize our utility function. And as I was saying, we are not choosing without a restriction. So we are choosing x and y subject to the second line, the budget constraint. So x and y must satisfy the inequality in the second line, which is that x times px plus y times py cannot be larger than our level of income, which is the budget constraint. So here, everything is quite abstract, but later on, you will see the form of the utility function. You will be given numbers, what the price of good X is, what the price of good Y is, and what your level of income is. And we will be able to solve this problem and find X and Y in numbers. But we are going to first approach this problem in the most general possible case. And before we actually get into that, I want to provide you with some intuitions. So when we were defining the indifference curve and when we were drawing it on the graph, we know that under the assumption that more is better, the higher the indifference curve, the higher the level of utility. Therefore, if we think on a graph, what we are looking for, we are looking for a point. Well, a point on a graph represents a consumption bundle, right? So we are looking for a point that is, first of all, it has to be within the budget constraint. And secondly, it is on the highest indifference curve possible. And to be on the highest indifference curve possible, it is giving the consumer the highest level of utility possible. Now, the second intuition is that, well, most of the cases we are concerned with are cases when the assumption more is better is satisfied. Therefore, under this assumption, the optimal bundle or our solution must actually lie on the budget line. Why is that? Imagine that if you claim a point that is not on the budget line is your optimal point, then that means that there are part of your income that is not spent on purchasing either of the good. I would argue that we can spend that unspent part of your income on purchasing more of either of the two goods, and because more is better, the consumer will be made better off in this case. Therefore, I will be able to find a point that is within the budget constraint and makes the consumer better off. This will invalidate your claim that the original point you find is the optimal point. Therefore, under the assumption that more is better, the optimal point or the optimal bundle must be a point that is on the budget line. And to translate this into equations, basically this is saying that the budget constraint, the second line, must hold with equality instead of inequality. And last thing, before we are ready to go, there are two types of solutions. We call them the first interior solution and the second corner solution. And we make this a distinction because the conditions we use to find those solutions are different. So let me draw a budget line here. So let's say we have a budget line that looks something like this. Now we know the budget constraint means that the optimal point has to be everything in this shaded region, right? We also argued previously that actually a point that is, well, not spending all your income is not going to be the optimal as long as the assumption more is better is satisfied. Because I can show it graphically here that if you claim this point is your optimal point, I will say that this point that is also affordable given the budget constraint. And because more is better, this point must provide the consumer with the higher level of utility than the point. So this is point A. Point B must provide the consumer with a higher level of utility than point A does. And point B is also affordable so that point A cannot be the optimal choice. Now, if we look at this budget constraint, the interior solution basically means that any point that is not on the two axes. So if we have an axis for grid X and an axis for grid Y, the interior solution means that a point that is not on the axis. So it's harder to mark the interior solution, but I will draw the corner solution here. The corner solution means that it's an optimal bundle at which some of the good is not consumed. So your consumption of grid X may be 0, or your consumption of grid Y may be 0. So the optimal bundle is going to lie on the axis. So the corner solution are basically some point along this y-axis. So I overdraw here. So it is some point along this part of the y-axis or some point along this part of the x-axis. Well, it's all right. I draw it in a curly way so that you can see it. And any other point that is in the budget constraint, but not on this horizontal or vertical axis marked by the red pen, it will be interior solution if it is a solution to the optimal choice problem. All right, let me actually clear this. So here I'm going to show you graphically how we can find our interior solution for a Cobb-Douglas utility function. And we know the shape of the indifference curves for Cobb-Douglas utility functions. We draw it in previous videos. So again, we have a two-dimensional space. On the horizontal axis is our grid X, and on the vertical axis is our grid Y. We know that the indifference curves of Cobb-Douglas utility functions look something like this. I've shown you a better looking graph in the previous video by drawing it using a computer. So here, this is as good as I can do. And we also know that the further away the indifference curve is from the origin, or the higher the indifference curve, the higher the level of utility, right? So let's say if this is U1, this is U2, and this is U3. We know that U3 must be larger than U2, and U2 must be larger than U1. Now, let's suppose the budget constraint looks something like this. So let's imagine the budget constraint. This black straight line is our budget constraint. And it intersects our indifference curves at several points. I'm going to mark them. It intersects our U1 at 2 points, here and here. It intersects our indifference curve U2 at exactly 1 point, which is here. So if this is point A, this is point B, and this is point C. And let me mark another point, that's point D here, which is on our U3, that is somewhat a random point. So, and to emphasize, although I only draw 3 indifference curves, there are many more indifference curves on this graph that I didn't draw. So there will be an indifference curve that is between U1 and U2, looking somewhat similar, and do not intersect with either U1 or U2. All right. So I'm trying to, and let's recall what we are trying to do. We are trying to find a point that is, first of all, within the budget constraint. And we argued that for it to be optimal point, it will lie on the budget constraint. So a point that is interior, for example, here, a point E over here is going to be out of our consideration. And we are going to focus on point A, B, and C, and point D will be somewhat relevant later on. So we are looking for a point that is on our budget line, and it is also on the highest level of indifference curve that is possible. So my first argument is that point A cannot be the optimal choice. First argument is that point A cannot be the optimal bundle. And probably you already know why I can make this argument. So if we look at point A is on the budget line, and it is on the indifference curve of U1. So we know that your level of utility of consuming the bundle A is U1. And we also know that U1 is smaller than U2, which is because U2 is a higher indifference curve than U1 is. And we also know that the utility of consuming the bundle B is U2 because the point B, the consumption bundle B, is on the indifference curve U2. So for U1, I can find a point, and in this case, it is point B. And what is special about point B? Point B is both within the, sorry, let me redo this again. All right. So my argument for my first statement that point A cannot be the optimal bundle is that I can find another point, point B, that is also on the budget line, so that it is in the budget constraint, and point B provides a higher level of utility than point A does. Oops, than point A. So this makes sure that point A cannot be the point that provides the highest possible level of utility. I can make this argument for point A, and I can make this argument for another point that's over here. Let's say this is point F. Or another point that is over here, let's say this is point G. And for point C as well, right? So any point that is not point B on this budget line, I can make this argument. And by making this argument, none of those points can possibly be our optimal bundle. And probably you can guess by now, the optimal bundle is going to be point B. As the budget line is tangent to our indifference curve U2 at point B, we will not be able to find another point that is on the budget line and also provides a higher level of utility than point B does. So any point that provides a higher level of utility than point B does, say a point like point D, is going to be outside of your budget, is going to be outside of our budget constraint, meaning that the consumer cannot afford to that consumption bundle. So graphically, what is special about point B is the point where our budget constraint is tangent to our indifference curve. So my second statement is that point B is the optimal bundle, and any point other than point B cannot be an optimal bundle because I can make the statement I made above here, the statement 1, to any of those bundles, because I can make statement 1 those points. All right. So what is special about point B? The third statement is what is special about point B So if we look from the graph, we can see that, so instead of actually saying what is special about point B, I should have said that what is special about the optimal point, the optimal bundle, right? So what is special about the optimal bundle? Instead of point B, what is special about the optimal bundle? Well, the budget line is tangent to the indifference curve at point B, which is the optimal bundle over here. And cross this out. All right. So this graphic intuition or illustration will help us to derive what we are going to see in the next slide, the condition, which we call the tangency condition, in finding the optimal bundle or the optimal choice. So clear my drawings here. So the solution or the interior solution to the maximization problem when your utility function is top orderless or something similar to that, we discussed in the previous slide from our drawing that it must satisfy the tangency condition. And then the tangency condition means that, well, when the budget line is tangent to the indifference curve, it means that the slope of the indifference curve is the same as the slope of the budget line. We derived in previous lecture videos, the slope of the indifference curve has a name for it, is the marginal rate of substitution of x for y, and that equals to the negative value of the ratio of marginal utility of x to the marginal utility of y. The slope of the budget line is also a negative value because both of them are downward sloping. It is the negative value of the ratio of the price of good x to the price of good y. So eventually, this tangency condition implies that those two slopes are equal, and we can cancel out the negative sign. So what we are left with is the tangency condition, that is the marginal utility of good x divided by the marginal utility of good y, equal to the price of good x divided by the price of good y. So here everything is abstract, but imagine if you are given a utility function, you will be able to calculate what mu x is, what mu y is. Also, px and py are some numbers that will be given to you, right? So with this tangency condition, we will be able to, well, we will not yet be able to solve for the optimal choice yet, but we will be able to find a relationship between good x and good y. We are going to combine the tangency condition with the other condition, which that is the optimal bundle must be on the budget line. So combining those two conditions, we are solving a system of two equations with two unknowns. The two unknowns are x and y. We will find the optimal bundle eventually, and I'm going to show the later on steps in the numerical example. Here we are describing everything in a more abstract way. And there is more intuition for this tangency condition. So we can rewrite our tangency condition a bit by moving the px to the denominator on the left and moving the marginal utility of good y to the numerator on the right. So what the tangency condition is saying is that those two ratios must be equal, and those two ratios are mu x divided by px and mu y divided by py respectively. So let's look at the unit of those two expressions. The unit of the marginal utility of good x is delta u divided by delta x. This is telling us how much increase in the utility would be if we increased our consumption of good x by 1 unit. On the denominator, px is basically the dollar you have to spend to consume an additional unit of good x. So the unit of it is the increase in the dollar amount divided by the increase in the good of X you consume. So we can not only divide numbers, we can also divide units. If we divide those two units, what we are left with is delta U divided by delta dollar. So what this says, this is telling us the additional utility you are going to obtain by spending the last dollar consuming good X. Although the delta X cancels out in this expression, but we are concerned of consuming good X here, right? So this is on the left-hand side. So on the right-hand side, it is the additional utility you are going to obtain by spending the last dollar consuming good Y. The tangency condition in this case would going to mean that the last dollar spent on consuming good X, well, sorry, the additional utility you obtain by spending the last dollar consuming good X has to be the same as the additional utility obtained by spending the last dollar consuming good Y. Imagine if those two are not equal. So imagine that the additional utility you obtain by spending an additional dollar on good X is higher than that of good Y. Then you probably want to decrease your consumption of good Y by a little bit because, well, the dollar spent on good X makes you better off, right? And increase your consumption of good X by a little bit. And if you make such adjustment, by consuming by consuming less of good Y, your marginal utility of good Y will become higher. Well, because marginal utilities are decreasing as your consumption of the good increases. And if you increase your consumption of good X by a little bit, your marginal utility of good X will decrease by a little bit. And after the adjustment, and recall that MUX divided by PX is higher than MUY divided by PY. After you make the adjustment, the left-hand side becomes smaller, the right-hand side becomes larger, and they may achieve the equality again. And you are effectively increasing your total utility because you are making this after you make this adjustment. Therefore, when we have a Cobb-Douglas utility function, the tangency condition can be interpreted this way, that the last dollar spent on consuming either of the two goods must yield the same level of additional utility, or otherwise you will not be maximizing your utility, for the reason that we can make the adjustment I described just now. Now we are going to look at how we find the solution for perfect complement. We are going to use the same idea as we did just now, that we are going to find a point that is on the budget line and that also gives the highest level of utility, or to say, that is also on the highest indifference curve. We have X on the horizontal axis and Y on the vertical axis. So recall that the indifference curve for perfect substitutes are L-shaped curves that look something like this I'm going to draw. And I'm going to first draw a supplement line that is going to be helpful for my drawing. So let's say this is a straight line. So the indifference curves are straight lines that has, oops. The indifference curves are L-shaped like this. With their corner points on this straight line. So again, the higher the indifference curve, the higher the level of utility. So we have U1, U2, and U3 here, and we are going to know that U3 is higher than U2 and is higher than U1. So now let's suppose we have the budget constraint is, well, always going to be a straight line, right? So let's suppose the budget constraint is a straight line that looks something like this. And let me also mark a few points that we are going to focus on. So the budget constraint intersects our U1 at 2 points, A and B. It intersects our U2 at its corner point, C. And well, it doesn't intersect our U3, but let's say a point that's here is D. So using very similar logic I used previously, we can argue that point A cannot be the optimal point, nor can point B, because we can find another point, that is point C, all of which are on the budget line. Point C is also on the budget line, so it is within the budget constraint. And by consuming point C, the consumer will yield a utility of U2 that is higher than U1. And U1 is what the consumer gets by consuming point A and or point B, right? And similarly, we can argue that point C is the optimal point because the consumer can not find another point that is also on the budget line but gives her a higher level of utility. Any point that gives her a higher level of utility, such as point D, is going to be outside the budget constraint. So by making such arguments on the graph, we can see what is the condition for us to look for the optimal bundle or the optimal consumption point. So what is special about point C is that point C is where our blue line intersects with our indifference curves. And this blue line are the traces of all the corner points of the indifference curves. And what's special about those corner points is that at those corner points, AX and BY are equal, or what's in the parentheses of our minimum operation are equal. So this blue line is actually represented by AX equals to BY. So I'm going to say that the optimal point or the optimal bundle are located at the intersection of the blue line and the indifference curves. This is what we have argued and what we have observed so far. So based on this condition, we are going to be able to find the optimal ratio. This will give us the optimal ratio of X and Y. And we are going to see the formulas in next slide in just a second. Sorry, optimal ratio. And combining, so see here, this does not depend on the budget constraint at all, right? So this is the intersection of our blue line and the indifference curves. So we are not taking the slope or the shape of the budget constraint into consideration in any way. So, and this only gives us the optimal ratio. We are going to combine this optimal ratio, which is one condition, with the fact that the optimal point must also lie on the budget constraint. That is the second condition. We're going to combine those two conditions and eventually find where exactly point C is. All right. So this gives us the optimal ratio, the optimal bundle is the intersection of our blue line the blue line describes the optimal ratio and the budget line. So the orange line is the budget line in our graph. So the intersection of these 2 points gives us point C, which is the optimal bundle. All right. So this is the graph for perfect complement. So, well, if we have the utility function, the general form, we already showed it in the previous slide. The optimal ratio happens when ax equals to by. We can write it of x in terms of y, or y in terms of x. Later on, when we have the numbers, we can substitute this. Sorry, we can combine this with the budget constraint, and effectively we are going to substitute either x or y into the budget constraint equation, and find, or to say we solve for the number of x and y. So in the previous two cases, we discussed the two special cases of utility functions or preferences. The first is coprologous, and the second is perfect complement. We used graph to show that how we can find the interior solution, the optimal consumption bundle that is an interior solution. However, in general, even if we have utility functions or preferences or the indifference curves that are not coprologous and perfect complement, but look somewhat similar to those, we might end up in trouble. And here I'm going to just provide you with some graphs of those. We are not going to discuss, or we are not going to talk on how technically those functions look like. So the first problem is that the solution may not be unique. For example, if the indifference curves, so let me draw the budget constraint first, actually. So let's say this is our budget constraint. And our utility functions may behave differently so that the indifference curves look something like this. So it is, well, sorry, it's not very well drawn. It is still going to be downward sloping. The marginal utility for each of the two goods are still positive. Okay, it's a little hard to draw, but I can do it. All right, this time it's good. So the last part is, all right, practice makes better, not perfect yet. So the the indifference curves might look something like this. And I'm going to draw the second one. And another one. All right, so the indifference curves may look something like this, so that we can actually find 2 points where our budget line is tangent to our indifference curve. In this example, both of those 2 points will give you the same level of utility, and actually this indifference curve, if it is U2, is indeed the highest indifference curve that you can achieve given this budget constraint. However, the solution is not unique, as both point A and point B are going to be the optimal bundle that we can find. Of course, the utility function that corresponds to such indifference curves will look complicated and weird, and we are not going to see it for the purpose of this class. But I just want to let you know that such scenarios can happen, right? So the solution might not be unique. And secondly, the second possibility is that the tangency condition may, instead of give us the optimal point, it may only give us what is called a local optimal. To show this, and similarly, let's suppose the budget constraint. Let's fix the budget constraint first. So let's say this is the budget constraint. Now, the indifference curves are going to look, well, different. So there will be an indifference curve. Sorry, it's not good enough again. All right, this is one, and the other one is going to be, well, it will not intersect to the first one, but it might look something like this. So these are two indifference curves. There are more I didn't draw, and I'm going to mark the 2 points that's relevant. This point, which is point A, and this point, which is point B. Let's say this is U1 and this is U2. And we know U2 is higher than U1. So if we only use the tangency condition by equating the slope of the indifference curve to the slope of the budget constraint, well, at both point A and point B, this condition is satisfied. But if we look at the graph, we would know that point B is not an optimal point, right? Because at point B, we can find another point that is point A, which is also on the budget line and provides a higher level of utility than point B does. So point B is only a local optimal, but not an actually optimal solution. However, point A is the actual optimal solution in this case, if the indifference curves look something like this. So the tangency condition is only a good tool when we have a Cobb-Douglas utility function, which makes sure that the indifference curves are going to look nicely as what we have been drawing so far, etc. And in general, we should not blindly apply the tangency condition to find the optimal points, because for at least 2 reasons, there may be more than one solution, and the second, the tangency condition may only give you local optimal. All right. So actually, let me clear the graph. And we are ready to move to the next type of solution, which is the corner solution. So we will find a corner solution when we have a perfect substitute utility function. And recall that corner solution means that the optimal consumption bundle lies instead of, well, it lies on one of the axes. And it means that the optimal choice of the consumer is to choose consuming either 0 units of good X or 0 units of good Y. And we are going to see why the consumer might make such choice. And as always, let's fix the budget constraint first. So when we have a perfect substitute utility function, we know that the indifference curves are straight lines that are parallel to each other, and they have the slope of the indifference curves depend on the ratio of A and B, right? So let's suppose the indifference curves are steeper than the budget constraint. So the indifference curves are going to be steeper. They are parallel to each other. And I'm going to draw a few more. Oops, the budget line is too it's too steep. So sorry, it's not steep enough. So let me erase the budget line and redraw it. So let's suppose the budget line is like this. So let me draw this again. It's okay. Let's say the budget line is like this, like this, and the indifference curves are steeper than the budget line, which looks like this. And the indifference curves are parallel to each other. All right, I've drawn 5 indifference curves. All right, and let's recall what are we looking for? We are looking for a point that is on the budget constraint and that it also is on the highest indifference curve possible. So if we look at this graph, and let me mark 3 points again. So this is point A, this is point B, and this is point C. We can imagine, we can observe that as we move away from point A towards point C, towards point B, and then towards point C, the level of utility the consumer obtains is increasing, right? And eventually, the level of utility is highest at point C, and we cannot find a point that is in the budget constraint and provides a level of utility that is higher than point C does. So, based on this observation, we would claim that point C is the point that gives the consumer the highest level of utility while still remains in the budget constraint, or to say that point C is the optimal point. So what is special about this optimal point? Or to say, how do we find it? Well, point C is the point where the consumer consumes, well, spends all of her income consuming good X and spends none of her income consuming good Y in this case. So what actually matters is the relative slope of the budget constraint and the indifference curves. So let me draw another set of indifference curves that are flatter than the budget constraint. And I'm going to use a different color, and hopefully it will not become too, yeah, I think it's still, you can still see this. So this is hypothetically speaking, if the indifference curves are the green lines, all right? Now, if the indifference curves are green lines, then consuming point C is giving the consumer the lowest level of utility possible for a point that is on the budget line. And if we move from point C towards point B and towards point A, the level of utility the consumer gets is increasing. And point A is the optimal point that gives the consumer the highest level of utility. Therefore, in this case, if the preferences are represented by the green indifference curves, the optimal point would be point A. So the difference is that in the first case, the black lines, the slope of the black lines are steeper than that of the budget line. And in the second case, the slope of the indifference curves or the slope of the green lines are flatter than the slope of the budget line. So if the slope of the indifference curve is steeper than that of the budget line, which are the black lines, the consumer will be consuming good X only and consume 0 units of good Y. Conversely, if the slope of the indifference curves are flatter than the budget line, then the consumer will consume good Y only and 0 units of good X. I'm going to describe the condition in the next slide in a more clearer way here. This is what our conclusion or what we can observe from the graph. So in the case of perfect substitute, it really depends on the relative steepness or the relative slope of the indifference curves and the budget line. So here we say that if the indifference curves are steeper than the budget line, the consumer consumes all good X and 0 units of good Y. And note that it's important that we are putting X on the horizontal axis and Y on the vertical axis. If we reverse that, the conclusion will become different, all right? And the opposite is that if the indifference curves are flatter than the budget line, then consumers will consume 0 units of X and spend all her income consuming good Y. We can use our intuition from the cobbler's case here again to think why the consumer is going to purchase only one good while 0 units of the other good. So when we make a comparison of the slopes, we can actually rearrange our equations, and we are making a comparison between those two expressions, the MUX divided by PX and the MUY divided by PY. Now, in the case of perfect substitute, the marginal utilities are constant. Price of good X and price of good Y are also constant that is given to you. So those two expressions are not going to change as X and Y changes. Those two expressions are constant and it is fixed when the utility function and the prices of the goods are given to you. That is saying that for every dollar, so if MUX divided by PX is larger than MUY divided by PY, that is going to say that for every dollar I'm going to consider spend on good X or good Y, the additional utility I obtain from that is higher if I consume good X. And this is true no matter how many dollars I've already spent on good X, and no matter how many dollars I've already spent on good Y. Then if this is the case, the consumer have the reason to spend all her income consuming good X only, right? Because every dollar spent on good X is going to make her better off as compared to if she spent that dollar on good Y. And if we change the direction of the inequality, the conclusion goes the opposite direction as well. So when we have perfect substitute preferences, our optimal solution is the corner solution, and it's a solution where the consumer consumes entirely one type of good and a 0 unit of the other type of the good. All right, I want to bring up a special case where you will also find a corner solution here. Note that this utility function is not one of the 3 special types that we have seen so far, right? It is not Cobb-Douglas, it is not perfect substitute, it is not perfect complement. If the utility function is u equals to x squared plus y squared, we want to first draw the indifference curves. The indifference curves for this type of utility function are actually a quarter of a circle. So if you, I'm not sure if you learned it in high school, the mathematical representation of a circle, a unit circle, on the graph is x squared plus y squared equals to 1. And that 1 depends on the radius of the circle. So here, if we look at different levels of utility, the graph for this is a quarter of a circle of different radius. So the indifference curves, oops. This is not good enough. The indifference curves in this case are something that's like this. So they are downward sloping because the marginal utilities are both positive, but instead of being bowed in towards the origin, they are bowed out away from the origin. Now let's suppose we have a budget line that looks like this. So let's say we have a budget constraint that looks like this, and I'm drawing it specifically to be tangent at the second indifference curve. All right. So if you see this question, but you didn't draw this graph, and if you apply the tangency transition that we have been using, we have introduced for the Cobb-Douglas utility function, what you might say is that, all right, the marginal utility of grid X is 2 times X. The marginal utility of grid Y is 2 times Y. This can help me find the marginal rate of substitution, which is going to be negative X divided by Y. I can equate the marginal rate of substitution to the slope of the budget line. So the slope of the budget constraint, or the slope of the budget line, and I can find some solution later on. And what the point you are going to find by applying this procedure is this point. You are finding the point where the indifference curve is tangent to the budget line, right? You are going to find this point. But let's see, is this point actually giving you the optimal level of utility? We can easily find another point that is, say, this point. So call this point A and call this point B. We can easily find another point B that is also on the budget line and is providing a higher level of utility than point A does, right? So if this is U1, this is U2, this is U3, obviously U3 is higher than U2 and it is providing a higher level of utility. So the actual optimal bundle to this type of utility function is also going to be a corner solution that might be somewhere here, depending on the slope of the budget line, of course. So given how we draw it this way now, it's going to be somewhere here. It's also a corner solution. So we can see that any other point that is on the budget line is not going to provide a level of utility as high as point C does. Point C lies on the indifference curve, U4, that is highest among all. So this is a somewhat special case for us, which you will also see a corner solution, even if, the marginal utilities are well defined and you can use the tangency transition to find a point, but the point you find is not the optimal point. The point you find is point A. It is way worse than point B or point C. And my conclusion for this slide is that so I would want to remind you that you should not blindly apply the tangency conditions, even if you see a utility function that has nice derivatives, etc. All right. So the tangency condition only works for Cobb-Douglas and some type of utility function, but we need to verify that. And without doing so, we cannot apply the tangency conditions to those. The ultimate idea of finding the optimal solution is to look for a point that is on the budget line, or to say that is within the budget constraint, and that is also on the highest indifference curve possible. And in this example, we are applying this process, this way of thinking, and we can see from the graph that the true optimal point should be point C. While if you blindly apply the tangency condition, what you will find is point A, that is no way an optimal consumption point. So now we have discussed in abstract and in general how those conditions look like. So now we are ready to tackle a problem with real numbers here. And we are going to do two examples. The first is for Cobb-Douglas, and then the second is for perfect substitute. I might ask Jasmine to do an example for perfect complement in her distraction section. So let's suppose the consumer's preference is represented by the utility function uxy equals the square root of xy, a simple example we have been using so far. And the budget constraint that depends on your income, your price, the price of both goods, are such that the income is $800, price for good X is 20, and the price for good Y is 40. So we know this utility function is Cobb-Douglas. We can use the tangency condition here. So, and I want to emphasize this, the utility function Cobb-Douglas implies that we can use the tangency condition. And this is a quite important condition because without this one, without the first part, using the second part is incorrect. Tangency condition. So the tangency condition says that we are going to equate MUX divided by MUY equal to PX divided by PY. So this tangency condition is simple in its form, but I spent the whole past an hour maybe explaining in what cases can we use this, and in what cases we cannot use this, and also the reason behind it. So by applying the tangency condition, we are going to solve this equation. So for this utility function, the marginal rate of substitution, or the MUX divided by MUY, but the absolute value of it is going to be y divided by x. So MUX divided by MUY equals to y divided by x. I am skipping many steps here because how to find this ratio was done in previous videos, and you can go back to previous videos to find those steps. You may also have those on your notes. And px divided by py is 20 divided by 40. And from this equation, this implies that we can find an optimal ratio of y and x. So the optimal ratio is going to be y equals to, well, x divided by 2. If we multiply x to both sides and do some simplification. So this is the first condition, the optimal ratio that we are going to use. Oops. All right, let me type this again. MUX divided by MUY equals to y divided by x. Y equals x divided by 2. And this is our optimal ratio. All right. So we are going to combine this condition, and the second condition is that the optimal bundle must lie on the budget line. So the optimal bundle must lie. And we argued that this condition holds because of the assumption more is better. And for this to hold, it must be that 20 times x plus 40 times y equals to 800. So the budget constraint must hold with equality. We have an equality sign here instead of inequality sign here. So this is our second condition. This is our first condition. If we combine 1 and 2, combining those two equations, and let me just rewrite those here together. We have y equals to x times 2. We have 20x plus 40y equals to 800. We are solving those two equations simultaneously, right? So we can substitute. So what we can substitute 1 into 2. 1 into 2. And if we do this, we substitute y equals to x divided by 2 into 2. What we get is 20x plus 40 times y, and we substitute it by x times 2 divided by 2, sorry, equals to 800. We can simplify this expression. This becomes 40x equals to 800, or that x equals to 20. So this is the optimal value of x that we find, the value of x in the optimal bundle that we can find by solving the equations. And this gives us the value of x. So lastly, we substitute x equals to 20 into either 1 or 2. Because both of them has to hold in for the optimal bundle, we can substitute our x into either one of them. So let's say we substitute it into 1, which is simpler. We can find that y equals to x divided by 2, and x is 20. So y is 20 divided by 2, so the optimal y is 10. So combining all of those, the optimal bundle is y equals to 20 and 10. So this is the procedure how we solve a Cobb-Douglas how we solve a utility maximization problem when the utility function is Cobb-Douglas. It involves some derivation of math and calculations. They are not extremely difficult, but they're also not extremely simple. If you find you are so practice more, there are practice problems. There will be practice problems in the discussion sections. Practice this several times or many times until you feel confident that you are familiar of the process of how to solve it. All right. So we can lastly draw a graph showing what we have done so far, and it is going to be look very similar to the graph that we have drawn previously in the general sense. Although now we can mark all the numbers here. So we have grid X and grid Y. And I'm going to draw the budget constraint again in orange line. So the budget constraint is an orange line. The slope of this budget constraint is negative px divided by py. And in our case, it is negative 20 divided by 40, which is negative 0.5. The x-intercept is the income divided by the price of good x. That is 800 divided by 20, which is 40. This is your x-intercept. Your y-intercept is your price divided by price of good y. So it is your income divided by the price of good y. That is 800 divided by 40, which is 20. So we can mark the intercepts of the budget constraint. Now we can draw the indifference curves. So we only need to draw the indifference curve that the optimal bundle is at. So the indifference curve is going to be tangent to our budget constraint at the optimal point. So it's not very well drawn, but I believe you can understand what I'm trying to do. And let's say this is the optimal point here. So at this optimal point, we know that this point is 20, 10, as we have solved for it. We can say that this is the optimal point. So this will be a graph representing our solution to this question. All right. So in the next slide, so in this slide, I did an example for Cobb-Douglas in the next slide, I'm going to do an example for perfect substitute. So when we have a perfect substitute, we know that we are going to look for corner solutions for reasons we explained in previous slides. So we are going to make a comparison of the slope of the budget constraint and the indifference curves. So in this case, the slope of the budget constraint, the budget line, is active px divided by py. For the given numbers, it is negative 5 divided by 2, which is negative 2.5. Sorry, of, not if. Slope of. And the slope of the indifference curves are determined by the marginal rate of substitution. In this case, it is MRS of x for y, which equals to the negative of mu x divided by mu y. And given this utility function, the marginal utility of x is constant. It is 2 if we take the partial derivative of our utility function with respect to x. And then the marginal utility of group y is also a constant, that is y, 1, sorry. So this MRS is negative 2 divided by 1, which is negative 2. So we can see that the slope of the budget constraint is steeper because the absolute value of this slope is larger. It is 2.5, that is larger than 2, the absolute value of the slope of the indifference curve. So the budget constraint is deeper than the indifference curve. And recall the graph that we have drawn. When the budget constraints are steeper, does the consumer consume all of grid X or all of grid Y? Well, if the budget constraint is steeper, say like this, and the indifference curves are not as steep, right? So the indifference curves will be something like this. They are flatter than the budget constraint. Then we can see, obviously, that the consumer will be most better off if she consumes entirely grid Y and none of grid X. So in this case, this point is the point where it is optimal. This is the optimal bundle. Over here. And well, let's mark a few points that are going to be relevant. So we want to mark every intercept of our curves with the axis. The budget constraint is 5x plus 2y equals to 100. This is our budget constraint. So if we spend all of our income consuming good X, we can consume 20 units of good X. So this point is 20. And if we spend all of our income consuming good Y, we can consume 50 units of good Y. So the point that I marked over here is actually 50. So 50 is the point over here. For the indifference curves, it is flatter than our budget constraint, and we argued that consuming 0 units of good X and 50 units of good Y provides the consumer the highest level of utility. We can also find another intercept that is relevant over here. So I'm actually going to erase the indifference curves that are not relevant. Those are not relevant, right? So we can also find the coordinate of this point. So how do we find this point? What does this point mean? This point is saying that how many units of grid X does the consumer need to consume to achieve the level of utility when she consumes the optimal bundle. All right. So answering this question helps us find the coordinate of this point. So let's see. Oops, this is 50. So when she consumes 0 units of grid X and 50 units of grid Y, her level of utility is 0, 50. And if we substitute into our utility function, this is 2 times 0 plus 50, which equals to 50. This is the level of utility consumes the optimal bundle, which is 0 and 50. All right, now to answer this question, it is asking how many units of grid X does she need to consume to achieve 50 units of utility. And she is consuming 0 units of grid Y. So this is basically asking for what value of X will u X 0 equals to 50. And this implies that we have 2x equals to 50, or to say that x equals to 25, which is higher than 20 units. And we know that even if he spent all his income consuming good X, she can consume only 20 units, and 25 units is not affordable on her budget. So this point, 25, is outside the budget line. So therefore, this is the overall graph we can draw for consumer problem when the preference is perfect substitute, or when the utility function is representing a perfect substitute preference. So if the relative ratio of those two changes, it might be the answer might be that it is the optimal bundle is that consuming all X and none of grid Y. So this depends on the relative ratio of the slope of the budget constraint and the slope of the indifference curve. All right. So we have finished describing how we can solve many of those questions for different types of utility functions. So the questions I asked before we begin chapter 3, that we are making some decisions in daily life, whether we go camping or go to the beach, or whether we eat outside, or whether we prepare food ourselves and go to a movie afterwards. And lastly, what kind of basket or what kind of bundle do we leave the supermarket with? We are essentially solving constraint optimization problems. So the constraint may not only be budget constraint. For example, go camping might be more costly than going to the beach. And even if I'm a person who prefer going to camping, I'm budgetary constrained, I'm financially constrained, I can only choose to go to the beach in the weekend. It might also be time constraint, that I have $10 which I can eat outside, or I can prepare food myself, which is less costly, and go to a movie. Well, say $20, $10 is not enough. But we can see that preparing food And going to a movie is going to cost a lot more time, while eating outside, same as we are spending the same $20, but eating outside is costing much less time. And if I'm time constrained, I might choose to eat outside, even if I prefer to prepare food myself and go to a movie afterwards, right? And in general, there will be many other different kinds of resource constraints, not only budget and time. And lastly, we have been analyzing problems between two goods, so utility functions of two goods. However, think of the context of a supermarket. There are hundreds of goods, and our bundle is going to be is going to describe how many units of each good that we produce of those hundreds of goods. We didn't analyze this question, but the trade-off we are making, we can imagine, is going to be the same. So if we are looking at what we are going to purchase from a supermarket, we are solving a problem that we have a budget constraint for the given price of each of the goods and then the total income we have, as well as we are finding a point that is going to be on the indifference plane instead of indifference curve, when we have more than two goods. That is going, so we are looking for a point that is within our budget constraint, but is on the highest indifference plane. And the indifference plane in a 100-dimensional space is only imaginable. We cannot draw it in our 3-dimensional space. So, but the process of making this decision is actually the same, right? So we are solving all kinds of constraint optimization problems in our daily life as a consumer, and completing this chapter 3 and 4, we have finally reached to a conclusion of it. So to summarize what we have done today, we first defined what is meant by solving a utility maximization problem. So we are looking for a consumption bundle that maximizes a person's utility while remains in her budget constraint. And on a graph, we are looking for a point that is on the highest indifference curve and also that is on the budget line. So we discussed how we can solve 3 special types of preferences. When we have a Cobb-Douglas utility function, we can use the tangency condition, which is based on that we are looking for a point where the slope of the budget line is the same as the slope of the indifference curve. This gives us the tangency condition, which we can use it to calculate an optimal ratio. And if we have a perfect complement preferences, we can directly obtain an optimal ratio. With the optimal ratio, combining it with the condition that the optimal point must also lie on the budget line, we can find the optimal bundle. And in those two cases, we will find an interior solution. And if we have a perfect substitute utility function, well, we are going to compare the slope of the budget line and the slope of the indifference curves. Depending on which one is larger, we are going to obtain a corner solution. We are going to obtain the optimal bundle as a corner solution. And the corner solution means that the consumer consumes either none of good X or none of good Y. And this is the end of chapter 4. Starting next chapter, we are going to derive consumers' demand curve. And well, we will talk more later.